Right. So let's get started here. Hi, everyone. This is the using motors and gearboxes presentation. Thank you for joining the summer series here. And I guess we'll get started right now. All right. So a little bit of background on me. I've been doing FRC since 2014. I was design and engineering lead for Team 5199 from 2016 to 2018. And ever since I graduated in 2018, I've been a design mentor, helping out the team and doing stuff like gearboxes. So basically, this presentation is mostly just going to be kind of me sharing my kind of personal, not necessarily opinions, but experiences with designing gearboxes. I tend to do kind of a seat of the pants kind of design philosophy in a lot of ways, just because we have such a crunch design season. But this is kind of just my perspective on the ways to design and spec your gear ratios and motors. So I guess we'll get started with the basics, just to quickly make sure everyone's up to speed. This is kind of your, also at the very end, I'll have questions at the end. I tend to move kind of fast, as you can already tell. But if you have any questions, please, put them in chat, and I will try to address them as they come up or at the end as well. So this is your basic motor. Input. You usually have about 2 input wires, your output shaft, and your mounting holes. Some new developments have been, brushed versus brushless motors. For a long time, brushed were, the most common in FRC, but now brushless motors are coming up. They offer, a little bit more efficiency and power, but they have a special controller. And we can go into this a little bit later if you have some questions on that, but I'll just kind of leave it at that for now. In your gearbox, it's composed of, 2 main parts. You have your motors and your gear ratios themselves. This is a 2-stage gearbox because you have your input stage and your output stage. Sorry, you have your first stage and your second stage. Your input gear is usually called your pinion. So if you see that in documentation, that's your small gear. Your big gear, sometimes called the bull gear, is usually the output. If you're gearing down, if you're gearing up, you'll be going the other way. So a common question I get from people is, why gearboxes, right? We have these electric motors. They're relatively powerful. So why do we need a gearbox? Well, electric motors in and of themselves usually have very high RPMs and pretty low torque at the actual output shaft. Like, I don't know if anyone's ever taken a raw electric motor, but I wouldn't recommend doing this, but you can actually stop it with your hand in most cases fairly easily with a small handheld motor. But you can put it in a gearbox and obviously it becomes much more powerful, much more usable. And additionally, the output shaft is usually relatively small, because the motor itself is fairly small. So it's kind of hard to mount to that. So in actually doing your gearbox, gearing is actually relatively simple. It's just based on the ratio of your small gear to your big gear, or, of the gears to themselves. They can be thought of essentially as circles of 2 different diameters. So when you put them together, you get kind of this ratio effect of the small and the big. And actually, very old reduction systems involved, just simply 2 friction surfaces that were just circles rolling together. Teeth were added, to prevent slippage, and allows you to transmit significantly more torque. So moving on from there, you can see that the gears themselves have different circumferences. This is what we're going to learn is called a pitch circle. And this is actually, kind of like the midpoint, the point where the 2 gears are tangent to each other. And this is equal to your gear ratio, right? So your radius is related to your circumference. So your circumference and radius are kind of combined and they equal your gear ratio. And you can see this small gear would have to move 2.375 times to match the distance of the green gear, right? The big gear, which means that this green gear will move 2.375 times slower than whatever your input is, right? So your output shaft moves slower than your input shaft because this needs to spin more, go farther than the big one, right? And so this is what gets you your speed reduction. Now, most of the time, speed reduction is kind of a byproduct to what I see as the ultimately more important part of a gear system, which is your torque change, right? So a gear, you can kind of think of it as two different levers, right? Because, torque is just a force at a distance from your rotation center. So if you have a small lever pushing on a bigger lever, you get more mechanical advantage from the input shaft on the smaller gear to the output shaft on the bigger gear. And of course, this works in the other way as well. If you end up, gearing to increase speed, you lose torque because now you have a longer lever pushing on a shorter lever, right? So you lose that mechanical advantage here. And so this is one of the major advantages to having a gear ratio at all, is that you can actually take these high RPM but very low torque motors and change them into a slower RPM but significantly higher torque output. And that's kind of the whole idea. So the key ideas when kind of thinking about gearboxes is power in and power out. This is what I found was the most important thing when I was learning. I was thinking, how do these small motors, right? Why can't I just use a tiny motor instead of, a big motor, right? If anything can be geared to any torque, right? Because theoretically, any motor can produce any torque as long as you gear it enough. Well, no matter what, the smaller motor will always have less power, right? So power in equals power out is one of the most important things, because you will never get a small motor that is extremely fast and has high torque at the output of your gearbox. You have to sacrifice something, right? There's no free energy in this equation here. So if you have a bigger motor, you can gear it down less, you maintain a higher speed while also outputting a similar torque. And we'll go into this a little bit later in the presentation when we go over actually kind of looking at calculations of the gear ratios. But yeah, the main thing is, there's no free energy in this equation. A bigger motor will always have a faster and higher torque output. Ratios are easy to calculate. Like I showed before, it's just a ratio between the input gear and output gears. So if you have a 20-tooth input gear and a 40-tooth output gear, 40 over 20, that's 2 to 1. Your speed will be halved because you divide it, and your torque will be doubled because you multiply it. These concepts also apply to belts and chain. So if you have, say, a 20-tooth pulley and a 40-tooth pulley, it's the same. It's a 2 to 1 ratio, and the same concepts apply here. So what are your options when you're kind of designing a motor for FRC, right? Well, there's only a select number of FRC legal motors. These motors are defined in the rules. It makes your life both easier and harder, I would say, because you have less of a selection, which puts you in kind of a difficult position because some of the motors, you just space gaps in between power levels and sizes and things. But it's also easier because you don't have to wade through a million different motors to find the one that you want. VexPro has a really nice list with really helpful data. You can find that at motors.vex.com. I would say that's, when you're designing a motor, that's a, one-stop shop, very easy, especially if you're buying your motors from Vex. They give this very helpful list. You can dive into each of these motors. They have really helpful graphs that we'll go over later. But yeah, we'll come back to that later in the presentation. Okay, so types of gears. There are what are called spur gears, right? That's your classic, if you look at a picture of gear online, you'll find, toothed, single plane, one gear touching another gear. that's your simple spur gear right here. It's easy to make custom reductions. Like I said before, the ratios are just equal to each other. Mini cocked gearboxes come with this. These gears are usually fairly large, but you make up for that with their high strength. They're relatively easy to package. I mean, this gearbox here, you can see it's just, 2 shafts on a plate. And they're often pretty cheap because they are such simple two-dimensional shapes. You can buy a lot of pre-made gearboxes with this configuration. Where you have your pinion gears as the one I showed before. And yeah, these are usually, kind of the more common option when you see teams make their own custom gearboxes. But if space is at a major premium, planetary gearboxes offer a couple distinct advantages, but also a couple drawbacks. The main advantages are they are extremely small and extremely low weight while they are dense, because you have a reduction that happens using this planet and sun system. I'm not going to go into that a lot right here, although I would encourage, looking a little more into the theory and calculations behind that if you want to later. But it's a very neat system that gets you massive reductions in a small space. In the same space, you can get a 3-to-1 reduction. You can also get a 10-to-1 reduction. But because of this, they are lighter duty, while you do make up for that with their space efficiency. But I wouldn't recommend using these for anything that has a high kind of impact output. And because you can see, they have a lot more moving parts and a lot of, small shafts in here that couple things. And just the movement is a lot more complex, so they can be significantly harder to repair if they're repairable at all. Oh, another interesting option you can think of are shifters. I'm not going to go into shifters and the selection of them right now, but it's basically just 2 different selectable ratios. You can see this is what's known as a dog shifter. It's a little bit simpler of the 2 options. You can probably make this with just a drill press and a simple mill, but you can easily see how it's just 2 different ratios that connect to each other. So you can use the same calculations that we showed before. And then another thing is a ball shifter. There's really one main COTS option, which is from Vex. These work in a different way. I would recommend looking into the Vex website if you want to see how these actually work. Once again, you're just selecting 2 different gear ratios, and so all the calculations that we show later in this presentation will also apply to the 2 different ratios in here. Okay, so the kind of meat of the presentation here are the design considerations. So once again, if you have any questions, make sure to leave them in the chat, and I can come back or I can slow down. But yeah, this is the most important part for sure. So the first thing to do at any state of the design process, and especially for gear ratios, is to define your loads on your mechanism, right? So in this case, what's helpful to have are, say, the length of the arm that you want to drive, or your drive wheel diameter and the weight of your robot if you're doing a drivetrain, or the pulley diameter if you're doing a elevator or climber if you're using like a rope system. These are all needed to calculate the gear ratio to find the force needed or the torque needed to properly move your mechanism, right? So torque is very important. Without torque, the robot will not move, and I'll go into that a little more in a second. So speed is the other option, right? So when you pick your gear ratio, you're balancing your desired speed and your needed torque, right? So what's interesting about this is speed, while it is really important to have, a high-speed mechanism, we're in a competition scenario. If a mechanism is geared for too high of speed and doesn't have enough torque, that mechanism will never move at all because the motor will not be able to move your load. So if it's the choice between having the speed you want and the torque you need, you always have to pick the torque you need because if there's not enough torque, the mechanism simply won't move at all, and that speed will essentially be unusable, right? So, in this case, oftentimes, the team will decide, a target drive base speed or a target elevator speed or an arm speed, and you will base your calculations off of all these in the future. So it's good to know what kind of your goals are so you have something to shoot for when you're designing. In terms of weights, you want to take into account everything that you can foresee, not only, the game piece, but also the mechanism, how much safety you want to give it, in case you might accidentally have a second game piece that you need to move out of the way, your robot weight, robot weight with pushing another robot, all kinds of things like that you want to make sure you consider. Something else that's important is kind of just general stuff, wear and impact. These can really determine which types of gears and gearbox you want to use. Like I said before, the planetary gearboxes, small and light, but also easily breakable and almost impossible to service on the field. So, you want to take that into account when you're designing your gearboxes. Additionally, same thing, you balance between your space you have versus, what you need. And sometimes, you have to go back and make sure that, your thing not only fits, but also won't break on the field. Something that's nice is almost all motors and off-the-shelf gearboxes have CAD supplied. So, make sure to use those when you're actually designing. A lot of times, you design your mechanism and you'd be like, okay, I'll just put the motor here. But, you want to make sure you actually put that motor in CAD in your design, draw it out at least in 2D, and make sure you can get enough space, especially if your motor is moving on, say, an arm. Another thing, there's many different motor sizes, and as I'll show in a minute, a lot of motors are, radically different sizes, but have the exact same power, right? So power in, power out, they have the same power, but you have to figure out, okay, would I rather use the larger motor and have a little bit easier gearing, or would I rather use the smaller motor? It really depends, if it's in a weight critical place. And this is really kind of where your job as a designer comes in to figure out what is ideal for your situation. So this is on, a case-by-case basis. And I'll show a calculation later using a calculator where you can really see the difference between a small high-speed motor and a large low-speed motor that have the same power, and what kind of difference that makes for your gearbox. Okay, so most important part, I think I said that before, but this is definitely the most important part of the presentation. If you take nothing else away from this meeting, you definitely need to check out the JVN design calculator. This is something made by, I believe his name is John V. Noon. He's from the Robo Wranglers. He has a great calculator. It's completely invaluable. It is the most important thing you could ever use when you're doing these quick iterations and calculations. It has lots of tables in there for all kinds of different stuff. You really don't have to, dive into the theory right away if you don't want to. You can just get an answer if you need one quickly. But once again, if I would encourage looking into the theory because it helps understand these calculations a bit more. It's to find this calculator, it's usually best just to Google, JVN gear ratio design calculator, because he does tend to update it as new motors come out, and especially recently as we've been having, kind of an influx of new brushless motors. He can, usually add those or update them. So I'll kind of go into how to use this calculator right now. It's very simple, but I'm just going to kind of provide an overview and then my process that I use when using the calculator. So the first part is to, you can kind of look at these different pages that they have in here for the different mechanisms. There are tabs for, linear mechanisms, rotary mechanisms, drive bases, all kinds of stuff. And you can see, just the amount of information that it gives. You can input your motor type up here. It'll automatically populate all these boxes. And then any of the boxes with the kind of red, orange looking color, those are actually inputs that you put in, your parameters in here. So you can see, this is why it's so important to know your loads before going in, because see, this requires, how heavy of a linear mechanism or how heavy of a robot do you expect to pull, or how long is your arm, what's the weight. And then additionally, this is where you actually play around with gear ratios down here. It also offers some easy configurations for commercial off-the-shelf gearboxes, mostly for just VEX products because they're kind of more related to that. But yeah, you can see, once again, you got to know your wheel diameters before going in, your friction, all kinds of different stuff in here. And then you just kind of iterate through and get your outputs. And we'll go over how to read these outputs in a second. Another thing that's nice is, you just look up, motors once, if you need to add a new motor, and you can put them in here and you can see all of these. You don't have to go to the website every time you want to see the motor specs themselves. They're all contained in the calculator. So as new motors are added throughout the season or between seasons, you can easily put them in here and they'll pop right in and all the calculations will be done for you. So now we get to the part where, you decide, which motor is actually good for your particular application. And this comes from, the outputs that it gives you. You have to verify the outputs and make sure it has your desired result. So you can see here, the outputs look, they look the same for most of them. They have a drivetrain output one, which will show your drivetrain's free speed. This is showing for a 2-speed gearbox with your different ratios here, and shows your expected robot speed. And then also for something like an arm or a linear mechanism, you can see what your max load will be and what your current draw will be. So something to keep in mind when you're reading, especially something like current draw or stall load, is that there are breakers on the robot. And so if you see this number, is over, say, 40 amps for the large breaker, you will end up blowing your breaker if you're constantly loading at 40 amps. So you have to keep that in mind when designing your gear ratios, is that while the motor will technically work at those, it may end up being detrimental to robot performance. Additionally, the stall load, that's where your mechanism stops moving at all. So if you see the stall load, it's not 28 amps at 754 pounds. It's 28 amps at the load you put in, and 754 pounds is where your motor will simply stop moving and the whole mechanism will stop. So your actual load should be much less than the stall load you see here. If it's too close, you run the risk of any kind of extra loading causing your mechanism to stop and or even burn out motors in some cases. So how do we actually determine what this current draw means for each motor? That is done through something called motor graphs. So motor graphs are something that are relatively important to read, that often aren't brought up when first designing motors. They really give big insights into motor performance and can help you determine where you want to gear your motor, because all motors like being in a certain area and don't like being in another area, as I'll go over in a second. And this can literally make or break your design, right? So motors, we all know they burn out. And sometimes it feels, kind of like a mystery as, why is my motor burning out here? It moves the mechanism okay, but it's getting really hot. And this motor graphs are a way to show you, a relatively accurate representation of what your motor will be doing at any given load. So to find these motor graphs, I'm going to be showing you how to do it through the VEX website from motors.vex.com. Often, if you're using a non-VEX motor, the graph will be given on the motor's data sheet, or they will just simply give you max power. And I'll show you in a second how you can estimate these graphs based on max power itself. So something to keep in mind here is that these are done by VEX. So, there are some non-VEX motors on here, like the Neo motor. And so you'll see slightly different numbers based on where you get your sources from. So just keep that in mind. It may be a good idea to take an average of those. But for right now, we're going to go over the 775 Pro motor, just because that, it's an interesting motor to look at, and they have a lot of good data on that motor. So when you're on motors.vex.com, you will see 775 Pro, and then if you click on that, it'll open up a page with all sorts of information, right? It'll show you the information that they found from their testing up here, the very basic information showing, their max power, current and stall current and torque, and then the actual motor graph itself, as well as some other really helpful information over here. This is kind of outside what we're going to be talking about here, but if you're wondering why the 775 Pro tends to burn out easily, these graphs are helpful to find out that information. But the motor graph is really what we're going to be concentrating on here. So if we zoom into that, you can see that it consists of lots of different kind of lines themselves. And so you essentially have 4 different graphs on this one graph. Efficiency is the red dotted one. I usually don't worry too much about that, just because we'll usually be operating in this region anyways, as I'll explain in a second. You can see that current is highest when your motor is locked, and your stall torque is also the highest when your motor is locked. But your power, and this is output power here, your power increases until about the midway point and then decreases as you get up to the highest RPM zone. So what's interesting about this is, okay, if I run my motor in this region, or if I run my motor in this region, it'll have the same power at any given point, right? Because it's a parabola. So which region do I want to be in? Well, if you take into account current, you can see that this zone is a lot safer for the motor than this zone over here. All right. So if I am running the motor at, say, right here, this looks like about 300 watts of output power at about 13,000 RPM, it's only going to draw about 40 amps. Whereas if I try to get 300 watts of output power at 6,000 RPM, that's going to be drawing almost 100 amps, which will almost certainly burn out your motor and will trip your breaker very quickly. So when you're designing a motor, you want to be operating it in this safe zone over here. And so what's interesting about all electric motors is they all DC motors pretty much have this same graph here, where there's a high power zone past and before will be at the same point. So you always want to kind of design for this part here. Okay, so let's say you want to verify your output using this motor graph, right? So we'll move into the calculator again. So you put in your physical constraints, make sure you're working on the right calculator, put in your motor, put in your gearing, and then you'll see your output right here. And so these are your most important parts. So if we zoom into those, you can see here, okay, here's your current and here are your speeds, right? These are usually the two, and your load. These are usually the things you're looking at when you're actually designing your motor, your gearbox. So once again, the speeds are important, but they're usually a byproduct of your kind of maximum load case here, right? So let's say we have this motor at 42 amps. And it's a mini sim motor. We want to see if this is in the safe zone of the actual motor itself, or if this is something that's going to burn out the motor, right? So we move to the motor graph, and we cross-reference our amperage and our motor graph. So if we come over here, we can see this is the current axis as well as the power axis. And so we'll find 40 amps. And we'll move over to where the 40 amps are on this line, right? Because this is our current line, right? So we know that at 40 amps, it'll probably be running around like 3,200 RPM. And then we move up and we find that, okay, It is in the second half of the curve, but it is quite near the top, right? So you can imagine if a load over the one that we put in before, it'll increase our current, and we'll start moving into the kind of more dangerous zone. We'll actually start losing power for our motor. So it might be better to actually gear our motor farther down on this curve. So that way we have, if a higher load comes in, we actually gain power to compensate for that load, as well as not risk burning out the motor itself. So these graphs are very important to read and are really helpful in designing a successful and also safe mechanism. This basically just kind of reiterates what I said before, but also, takes into account, if your motor's too small, you may never actually get the performance you want out of it, right? So any motor can operate with enough torque in its safe zone. However, its speed will suffer if its power is too low. So that's, when you're sizing your motor, you really want to figure out what your lowest acceptable speed is. And that way, if weight is important, you can pick a smaller motor and use its power to the fullest. Whereas if you oversize your motor, you might be having something that's too unusably fast anyways, and is just increasing weight. So that's something to keep in mind when you're designing that. Same thing with efficiency. I'll show this in a second too with my example, but your input and output RPM, right, as I mentioned at the beginning of the presentation, they're based on your gear ratio, but they're also based on your motor. So if you have a very high RPM motor and a low RPM motor, then what's going to happen is you're going to have to gear down the high RPM motor more to get the same output speed as the low RPM motor. And that can lead to kind of some interesting problems, because some motors have the exact same power but higher RPM, and I'll show that in a second. Same thing with efficiency. So you want to make sure that you pick gears based on what you're kind of working on. I mentioned planetary versus spur before. Custom versus buyout. This is a big one. If you don't have the time to design or the resources to design an actual custom gearbox, it can be useful to just buy one out, but you still want to know do I want a planetary or do I want a spur gear, and then additionally kind of weight considerations and strength that go along with those themselves. Let's see here. Oh yeah, once again, make sure to check in CAD. This is an issue that we've run into before on Robot Dolphins. Is it looks like it's going to work, and everything seems like it's going to work, and you put it in CAD, it doesn't quite work, and that's why it's really important to make sure your space constraints are met when you're designing that. And then another thing is iterating. So usually you'll never get the gearbox perfectly right on the first try, or your gear ratios right on the first try. That's the beauty of using the calculator that I was showing before, is you can easily go back and keep changing your gear ratios with a couple keystrokes, and you can really tune in your gear ratio along that motor curve. So you can see if we are designing something that we know will have a constant load, it might not be good to be this far down the curve because you're not getting maximum power. Whereas if there's something where you don't expect getting a higher load and getting pushed back in the curve, then you can easily design for up here and extract more power, more speed out of your motor while still maintaining enough torque to actually move your mechanism. Okay, so I'm going to give a quick example, and then we'll move into some questions after this. So in this example, we're going to be doing a really simple robot arm. I'm going to kind of simplify things here and say, only brushed motors. We're going to use a 775 Pro and a Sim. We're going to compare those two for this example. We're lifting a 5-pound game piece with a 20-inch long arm that weighs 15 pounds, right? And we want to say, okay, speed is important as always, so we'll try to maximize that. So looking at the 775 Pro and the Sim, the sizes are kind of deceiving here just because of the picture, but the 775 Pro itself is a significantly smaller and lighter motor than the sim. And you can see this reflected in the free speed. This is a significantly higher speed motor. It has a lot less inertia on its rotor inside, and so it spins up a lot faster. Whereas the sim motor is a lot slower, but it has a higher initial torque. But what's interesting to note is while these motors are, massively different looking, their power is almost exactly the same. They're within, a couple percent of each other. This is only 10 watts more than this. And so it's interesting to note, looking at maximum power, what is going to be the difference in these motors when you're actually designing your gearbox? So we'll plug it into the calculator. And you see when you plug it in first, you just select from the drop-down menu, puts in all the information here, and you can see right away why we need a gearbox, right? The stall load for this thing with our arm length and our arm load will only be, a fraction of a pound, right? Because of the torque disadvantage that we have because of the arm length. So we need to start playing around with gearing and see what we can have happen. Something interesting that you'll note is that I actually didn't put, 15 plus 5 here. I actually doubled that. And that's because I'm adding a 2x factor of safety. Another thing to note is technically because of the way that the weight is distributed along the arm length wouldn't actually be 20 inches. But once again, for safety, I'm leaving that higher because that'll increase the load that's seen in the calculator, and we'll just kind of add a safety factor to your mechanism. That's something that you can change if you need a little bit more accurate performance, but I like to do this just to be safe. So you can see I've now geared these to have basically the same current draw per motor. But what's interesting to note is that look how much higher the gear ratio has to be for the 775. It has to be 440 versus 135 for the sim motor. And this can be interesting when you're trying to design a spirit gearbox because you'll probably have to add a lot of extra ratios in here. Now you can see here I've just simplified it and just used planetary gearboxes, but planetary gears often aren't the strongest for something like an arm. And if you're seeing that you might take impact, it might not be a good idea, especially to use a high gear ratio on the output. So in this case, if you had to use a planetary gearbox, might be a better idea to go with the sim because you can get that lower output ratio here. However, in most cases, you'd probably want to use the 775 because of its lower weight, even though you probably have to gear up more. And that's really something that is dependent on kind of your robot goals and your packaging requirements. But it's just interesting to note that they have the exact same speed, exact same current draw, almost exact same stall load, but it's the gear ratio that really drives the difference here. Whereas, power is the same. And so kind of last thing I'm going to go into here, I'll go through this quickly just so I have enough time to answer a question or two. Basically, when you're designing a gearbox, it's relatively easy to actually prototype your gear spacing, right? Because gear spacing is extremely important. So gears, once again, are just basically circles. And there's a specific name for this, quote unquote circle, and that is what's called the pitch diameter. You can find these, on your manufacturer's website. And so you want to make two circles that are equal to the pitch diameter of the gears and make those circles tangent to each other. And so I'll show you how to do that really quickly. So this is the Vex Pro datasheet. You can see here the pitch diameters are all given, and they're just, it's a diameter of the circle. You can see the pitch diameter is represented as this inner circle here. And so if I wanted to say put a 20-tooth gear with like an 80-tooth gear, or 24-tooth gear with an 80-tooth gear, I just take those pitch diameters and make two tangent circles, and that gives me my center to center distance between those two shafts. And so this is, you just got to keep this distance rigid to each other, and that's basically how you design, how you properly mesh these two gears together. Now you can play around with different meshes to get, different kinds of things like backlash or wear considerations. But once again, for just an intro thing, I think this is the key to, simply putting two gears together. All right, so I'll answer some questions quickly so we don't run too far over time. Okay, so when would you use 32 DP gears versus 20 DP gears? Okay, so DP is your diametrical pitch. That's basically saying, we have, these two circles, but how many, if you can put a lot of teeth on here or fewer teeth on here, right? And so you can imagine with a 32 DP, you're putting more teeth per diameter increase, right? So your teeth are smaller. So you can get a lot of teeth on a really small gear. Let's say you want to put it on a 775 shaft, right? You can get, say, more teeth than you'd be able to with a bigger gear or with a bigger DP, with like a 20 DP. But you sacrifice strength because each individual tooth is smaller. So usually you'd use a 32 DP gear when you want to have a gear that's physically smaller with a smaller shaft size, but strength isn't as important. Okay, so another question, is there a good way to remember which motors go with different mechanisms? So that's kind of a hard question to answer because, motors are so dependent on the actual mechanism. But a good rule of thumb is if you want to avoid gearing down, go with a larger motor like a sim or a sim equivalent. But if you have, something where your motors might be stalling out a lot, that's good to have. But if you want something to run high speed, say a shooter motor, you want to pick a higher speed motor for that, such as a 775 or like that new 550 motor that just came out. All right. There's no other questions. I believe that's it for time. We will be back in a minute with the mentoring to make a competitive team panel. And I'd just like to thank you all for coming to the summer series today.